Hello everybody, welcome to the lecture for today, April 24th. Today we're going to finish up the topic of classification of groups of small order by growing up to groups of order 8. And in this week's homework, you'll be doing groups of order 10, which is much easier than 8. It's very similar to 3, in fact. 6. Before we can list all the groups of order 8, I need to give you 2 more examples of groups. So what are the 2 examples of groups that I'd like to discuss? Well, the first one is specific to order 8, and it's called the group of quaternionic units. Oops. So quaternions are a much bigger thing. You can actually add and subtract these things with coefficients, and if you've taken calculus 3, this may seem similar to you if you've taken vector calculus, or familiar to you what I'm about to discuss. So the usual notation for quaternionic units is presented in the following way. So I have plus or minus 1, plus or minus I, plus or minus j, and plus or minus k. And in calculus 3, usually I, j, and k represent these vectors that are point in a given direction. And when one of the things you discuss in this course is the cross product of vectors. And that's going to be our multiplication here, basically. So what happens when I take the cross product of I with j, you get k. With j with k, you get I. And when you take I with k, you get minus j. These relations, usually I cross I is equal to 0, so we don't want to do that in a group setting. So instead we're going to define I squared equals j squared equals k squared equals minus 1. And the reason that we do this is because we want it to act like the complex numbers, right? So if I just take 1 minus 1, I minus I, then this is a subset of the complex numbers minus 0 with multiplication. And in fact, this is a subgroup of the complex numbers with multiplication when I take away 0. Because the only number I can't divide by in the complex numbers even is 0. Every other complex number I can take 1 over that and get the inverse, the multiplicative inverse. And you can prove that this is a group. It's in fact just a cyclic group of order 4, right? I squared is minus 1. I times minus 1 is minus I. I times minus I is minus minus 1, which is 1. So it's a cyclic group of order 4. And j and k will also generate cyclic groups of order 4. And they have this interaction here, which tells you how those cyclic groups interact. So for now, this is just an important group to think about. It's very special to order 8, and for a while, quaternions and the study of quaternions were the main competitor for linear algebra to model a lot of things in physics. So quaternions are very special. They have a lot of interesting properties. And this is an example of a group of order 8. You can check that these multiplications turn it into a group. And once you have these rules, then you can recover all of the complete multiplication table just using the group axioms. Okay. So that said, let's talk about the other group that I want to talk about before we start classifying groups of order 8, and that's in general the dihedral groups. So I've talked about the dihedral groups in a few of the problem session groups, but I want to talk about it briefly here, and I'm happy to talk with anybody about it afterwards as well. This is actually covered in chapter 4. I think it's section 4.3. Yep. So are the quaternions, actually. That's also covered in section 4.3. So it's this section 4.3.4 is groups of symmetries of geometric figures, and this has information on the dihedral group. I'll be focusing on the dihedral group of a square. which we'll be talking about in just a second. There's also the quaternions are discussed just a few pages previously. So this is the quaternionic group. You can see the full multiplication late table listed here. I don't want to list it out in the lecture, but if you're interested in the quaternions, he gives a bit of a history here as well. So they're a very nice group to think about. Okay, let's return to dihedral groups. So what is a dihedral group? What do? I take a regular n-gon. So n is the number of sides of my polygon. So a regular 3-gon is an equilateral triangle. A regular 4-gon is a square. A regular 5-gon is a regular pentagon, and so on and so forth. And I just look at all the symmetries of this thing. So all the ways to transform it and keep it in the same shape. So let's think about an example of this. Let's look at D4. So D4 is going to be the set of symmetries of a square. So here's a square. I've drawn out a little square. And I've got a second one here that we'll see will play an important role because we want to see how to transform this first one. So I need to keep track of the references. And I've labeled the corners according to colors. So green, blue, black, and red. And so what are the possible things that I can do to the square to keep it a square? Well, one thing I can do is I can rotate it around the center by 90 degrees. And it's still a square. I've rearranged where the corners are, but if I start with a square and I rotate it by 90 degrees, it's still the same square in the same position. So this is one of the symmetries of the square, rotation by 90 degrees, or pi over 2. And this is one of the generators of the symmetries. What's another symmetry I can do? Well, I can take the square, I can pick it up, and I can flip it across its horizontal axis. Right, so green goes to the bottom left, black goes to the top right, and these two also get flipped. And even though the top and bottom of the square, the top and bottom got flipped, the total effect is to still have a square in the end. I've just rearranged the corners. So this is going to be the other generator of our group, which is the reflection across the horizontal line. And it turns out that D4 is going to be a group of order 8. And in general, Dn has order 2n, 2n, yeah. So what's the full set of elements? Well, I can take all possible rotations, right? So here I have, let me get these configured in the same way to start. If I rotate by 90 degrees, I can also rotate by 180 degrees or 370 degrees. And then if I do a full rotation, I haven't done anything to the square. So the map that takes this square to this square is the identity. This one is rotation from this square to this square is rotation by 90 degrees. From this square to this square is rotation by 180 degrees, 270. So you can see that the group generated by rotation by 90 degrees is a cyclic group of order 4. And then I have each of the reflections, right? I have the horizontal reflection we talked about last time. I have the each of the diagonal reflections. And then I also have the vertical reflection. Okay. So now let's just do an example of a group multiplication. Let's see what happens when I try to do f sub L1 times r sub pi over 2. The group operation here is composition. Oops. So when I do rotation by pi over 2 and reflection across the horizontal line, right? L1 is the horizontal line. I should get another one of these group elements. So let's see what the total effect of doing these things are. So the first thing I do is I rotate my square. Gotta get it. Oh yeah, this is set up right. So I rotate my square by 90 degrees. And then I do a vertical reflection, a reflection across the horizontal axis. So I swap this and this and this and this. So what's the total effect of this? Well, black stays the same. Red gets sent to the opposite corner. Red and green, in fact, get swapped, and blue stays the same. So this is what happens when I reflect across this diagonal axis, right? The total effect. Let's see it one more time, how this works, right? I rotate by 90 degrees, and then flip across the horizontal axis, and the total effect is the same thing as just reflecting across the diagonal axis. So when I compose these two transformations of the square, I just get reflection across this line, which is L4. So it's the flip across L4. And I encourage you just to do it on your own. These are very easy to make. You just have to label the corners, and it's important that you label it so that the color on the bottom of your square is the same as the color on the top of your square in each corner. So this corner is black on both sides. And you can do similar computations just by hand using these cutout squares. So I encourage you to do it on your own. It's good to have a reference square to keep track of where this one started, because when you start doing it, it's hard to remember, oh yeah, black started in here already. So I encourage, this is a very good thing to do just to practice computations in dihedral groups. And you can make equilateral triangles as well and practice that, and pentagons, hexagons. Pentagons are kind of hard to make. Hexagons are the next easiest one, but they're still a little tricky. So squares are really the easiest dihedral group to do computations in, I would say, using cutouts like this. Okay, so I hope the dihedral group you at least have a good understanding of. Notice that each of these reflections is an order 2 transformation, right? That's one last comment I want to make. Because what happens, for instance, if I reflect across the vertical axis here? So I reflect, and then I reflect again, and then this is the same, the square is the same as what I started with. And if I reflect across the diagonal, and then do it again, I just swap these two positions, and then they get swapped back again. So each of these are order 2 elements, and each of these are order 4, and this is order 2. So every element has order 2 or 4, which makes sense according to Lagrange's theorem, right? D4 is supposed to be an order 8 group, so every element should have order 2 or 4. And these reflections are a coset of this subgroup. So this will come up in our classification later, that we have a subgroup of order 4, and we have a coset of this subgroup, which is the 4 reflections. And they're all order 2. Whereas in the quaternionic group, here's a subgroup of order 4. Here's its coset, right? If I multiply these by j, then I get j minus j, and when I multiply I times j, I get k, so a k and minus k. So this makes sense. This is a coset of this one, but these are not all order 2, right? Some of these are, this and this are both order 4. So this is a difference between the two groups. They both have order 4 subgroups, but their cosets satisfy different properties. Okay, so let's go on to the main event of the day, which is classification of groups of order 8. So to start the classification, what do we want to do? We want to break into cases. So as we know, every non-identity element has to have either order that divides 8. And it can't be 1 because it's not the identity. The only element that has order 1 is the identity element. So one of the simplest cases will be when every non-identity element has order 2. There's only going to be one group that satisfies this. And it's going to be very similar to what we did with groups of order 4, when every non-identity element had order 2 there. So basically, what I want to do is I want to choose distinct elements A and B. So B cannot be equal to A inverse because A inverse is equal to A. It has order 2. Therefore, A squared is equal to the identity, so A equals A inverse. A is exactly the element such that when I multiply by itself, I get the identity. So because these are distinct, A is not equal to B is not equal to A inverse or A. And A times B has to have order 2. So AB squared is equal to the identity, because every non-identity element has order 2. So if I bring, this is AB times AB equals the identity, so I can bring B inverse A inverse over to the other side, and B and A are both equal to their own inverses, right? Because every element has order 2. So B inverse equals B, A inverse equals A, and the important thing is that A and B commute. So in fact, this shows that any two elements of G commute, that G is abelian, once every element has order 2. And in fact, you can show that this group here, this set, is a subgroup. So now I choose C, and it's not difficult to show that when I multiply this set by C, I get a coset, right? Because if this is a subgroup, then these multiplication of each of these things by C has to give me a coset. And this is Z2 cross Z2 cross Z2. This is the only group where every element has order 2. Right, and A is going to be the generator of this copy of Z2, B is going to be the generator of this copy of Z2, and C is going to be the generator of this copy of C2. So one of the important things in this proof, A and B could be any two distinct elements, but C, you couldn't choose A, B, and C to just be three distinct elements because you need C to not be equal to AB as well. So you need to find the subgroup generated by A and B, which is Z2 cross Z2, and then build its coset. It's an exercise to show that this, in fact, is a subgroup of G once every element has order 2 and it's abelian. So this is sort of the less interesting case, the case when every element has order 2. And so Z2 cross Z2 cross Z2 is one of the subgroups in our list. And let's just make a list here. Z2 cross Z2 cross Z2. So let's move on to the next easy case, which is what happens when there exists an element of order 8. Well, if there's an element of order 8, we know what to do, right? G is just Z8. I take that element, I look at the subgroup generated by it. It's a cyclic group. Every cyclic group is isomorphic to Z sub that thing. So Z8 is one of the isomorphism classes of groups of order 8. And if there is an element of order 8, then G has to be isomorphic to this thing. Okay, so now I've got two elements in my list. So what's the interesting case? The interesting case is when not every element has order 2, and there does not exist an order 8 element, which means that there exists an order 4 element, but not an order 8 element. And this will be the difficult case, and this is where the quaternionic group and the dihedral group will both appear. And in fact, there will be one more group as well. So what do I want to do? To analyze this case, I know that there exists an element of order 4, so I can take it, and I can look at this subgroup. Now, once I have a subgroup, I can take a coset. I choose any h that's not in this thing, and I build the coset just by multiplying on the left by h. So this thing has to be a coset of this subgroup. And now I've listed 8 elements. So G is the union of these two cosets. I have the identity coset of the subgroup, which is just the subgroup itself. And then I have the coset, which is H times that subgroup. So I've listed G. Now I just need to determine how the multiplication on G works. And there are going to be many cases to consider. And I want to analyze the cases based on what H squared is equal to. Right? H is one of these things. When I multiply H by H, I have to get back into the identity coset. Right? If H times H was equal to one of these things, then I could cancel one of the H's, right? And get that H is a power of G. And I know that H is not a power of G. Right? So H times H is equal to HG to the K. What would happen if this were the case? Well, I could multiply by H inverse on both sides, on the left, to get that H is equal to G to the K, and this is not good. So I know that when I multiply H times H, I have to lie in the group, and it can't be one of these, so it has to be, it can't be one of these, sorry. So H times H has to be one of these 4 elements. So let's do the easy cases first, which is 2 and 4. Right? Case 2 is when H squared is equal to G, and case 4 is when H squared is equal to G cubed. And in this case, we'll actually be able to prove that our group was cyclic, and so we can rule it out. Because we don't want to prove, we want to assume that our group is not of order 8. Is not a cyclic. It does not have an element of order 8. And I do this just by computing the order of H. So in case 2, when H squared is equal to G, then when I look at the cyclic subgroup generated by H, I get the identity H squared is equal to G, multiply by H again, I get HG, multiply by H again, the H squared can be, I can substitute G again, so I get G squared, HG squared, substitute the H squared again to get up to G cubed, HG cubed, and then multiply by H again, I get H squared G cubed, which is G times G cubed, which is G to the 4th, and since G has order 4, G to the 4th is equal to the identity. So H is like, this is saying that H is a square root of G, and since G has order 4, if H is a square root, then H should have order 8. And this is a contradiction to our case, right? Because what are we trying to assume? We're trying to assume in our remaining case that there is an element of order 4, but no element of order 8. So case 2, I can get rid of. By an identical argument, since G cubed has order 4 in the subgroup generated by G, the cyclic subgroup, right? Because 1, G squared, G cubed squared is G squared. G squared times G cubed is G to the 5th. Mod 4 is G times G cubed. Gets me the identity. So G cubed is an order 4 element. So we can do the same thing. It's good practice for you to do it, in fact, and show that if H squared is equal to G cubed, then H still has order 8. And this is a problem. So cases 2 and 4 don't happen in this setup. So now let's turn to case 1. That H squared is in fact equal to the identity. Well, now I have subcases actually. So in case 1, when H squared is equal to the identity, now let's try to figure out how G and H interact. Right, I know how H interacts with itself. I know the order of H, it's 2. So let's try to figure out what G times H is here. Well, G times H again, for similar reasons from before, it can't be equal to the a power of g. Because if g times h were equal to a power of g, then multiplying this by g inverse on the left, I'd get h is equal to g to the k minus 1. And by assumption, h is not this thing, so this can't happen. So g times h is not a power of g. It's not a power of g, so it's not one of these four things. So g times h has to be equal to h times g to the k for some k. So now let's look at our subcases. Right, now we're going to classify based on what k could be. Well, I claim that k can't equal 0, because if k equals 0, then g times h is equal to h, and that would imply that g is the identity. And this isn't true because g has order 4. So k cannot equal 0. What happens if k equals 1? Well, then g and h commute. gh equals hg. And you can prove that once g and h commute, g is going to be isomorphic to z4 cross z2. So what's the isomorphism given by? G to the k, h to the l times g to the k is going to correspond to, in the bijection, right, an isomorphism is a bijection, kl, which belongs to z4 cross z2. Right, because g and h commute, when I multiply two of these things together, I'm just going to be adding the exponents. Right, and h here, according to this, has order 2. So that's why the L component is the z2 component. And g has order 4. So you can check that this map is well defined, that this association is well defined, and it's a bijection between my order 8 group and this order 8 group. So this is one of my cases. When k equals 1, I get the group z4 cross z2. And now we're done with all the abelian groups. All the groups from here on out will be non-abelian. So things won't necessarily commute. So now what happens when k equals 2? Well, if k equals 2, then I know that g times h is h times g squared, right? That was exactly the case that I'm in here, right? G times h is h times g to the k, so g times h is h times g squared. And now I multiply by h inverse. And what I've constructed here is a conjugacy equation. This is a common trick. This is an element that's conjugate to g squared. So g is conjugate to g squared. And we'll prove that this, in fact, can never happen. But we'll see it just in the special case for this proof. So why is this a contradiction? Well, what happens when I square this element? Let me do this computation more carefully below. H inverse g h squared. Well, why is conjugation so nice? Well, it's because when I start taking powers, I don't pick up h's on the inside. H inverse g h times h inverse g h. So this is going to be, the h and h inverse cancel. And then the identity element cancels as well. So I just get h inverse g squared h. And by induction, if I multiply by h inverse g h again, the h and h inverse will cancel, so I just get g squared times g. So in fact, by induction, you can prove that h inverse g h to the k is just h inverse g to the k h. And this is why conjugation is so nice, is because it basically takes powers to powers. So this element squared is equal to the identity. Now what's going to happen? I can move this h inverse over to the other side and get that h times g squared is equal to h. But these can't be the same elements because they're different elements of this coset. H times g squared cannot be equal to h, so k, it's impossible for k to equal 2. Basically, the problem here is that whenever I conjugate by an element, its order has to stay the same. So g squared is an order 2 element, and g is an order 4 element. So they cannot be conjugate. If two elements are conjugate, they have the same order. Okay. So, now what? The last case is k equals 3. So I get that gh is equal to hg cubed. And what I want to prove is that this is the case when we get d4. And let's prove this. Well, let's see why this is. Right, I have two generators, G and H are my generators. And by assumption, H squared is equal to the identity, right? So H is going to correspond to one of the reflections. And let's do a little computation in the dihedral group. Again, put these things here. So G here is going to be the rotation by 90 degrees, so it's the action where I turn this way. And H is going to be which reflection? Well, let's see. So I want to be able to turn and then do the horizontal reflection, I think. And what's the total effect of that? That's to swap these two. And I claim that this is the same as what? First, oops, right? So what's on the left-hand side? H is the reflection, and G is the turn. So first I reflect, and then I turn by 90 degrees. So what's the effect of this? It's to swap these two things. Now what's the other way to do it? The other way is to turn the opposite direction, right? Turn by 270 degrees, which is the opposite direction, and then reflect. So if I turn in the opposite direction and then reflect, the total effect is still to swap these two positions, right? Red and green. So this relation holds if G and H generate the dihedral group. And in fact, you can reconstruct the entire multiplication table just from this relation that H squared is equal to the identity, and that G to the fourth is equal to the identity. So let's just do a bit of it. Maybe we'll do the whole thing, I don't know. The problem is that the multiplication table is going to be huge, right? So I have, this is the rotation subgroup. And then what do I have? I have HG, and each of these computations well, in the actual dihedral group, the computations are quite complicated. But with the rules, they'll be a bit easier. So HG, HG squared, HG cubed. And so what do I know in these cases? I know that G has order 4, so G to the fourth is equal to the identity. H has order 2, because H squared is equal to the identity. We're in case 1 still. And I know that GH is equal to HG cubed. So for instance, I can fill in this first row just because multiplication by the identity gives me back the same thing always. Now this will be my left hand and right hand multiplication, right? So G times this, well, this is a cyclic group, so I just increase the index by 1 and wrap around to the identity. So that's easy to figure out. So let's figure out what GHG is. GHG is, well, I can use this relation to push my h to the left-hand side. This is hg cubed times g. G cubed times g is g to the fourth, so this is just h. GHG squared, well, it's the same thing as this, but there's an extra g on the end. This is hg, and this is, oop, I forgot to include h. H itself. So I put another g on the end, I get hg cubed, and then I have h here. G times h, we just said, is hg cubed. And you can do the same thing for each of these rows. Let's do one more row. G squared is just going to, this is a cyclic group, so this is nice and easy. I just fill in, right? G squared times g is g cubed. G has order 4, so g squared times g squared is the identity, and so on and so forth. Let's do g squared times hg. Well, I want to put it so that the h is on the left. So I can use this relation to push one of the g's over. Right, let me do it slowly. GGHG. So this is g times hg cubed g. G cubed times g is just g to the fourth, so it's the identity. So this is just gh, which is, as we saw, gh is hg cubed. Hg cubed. And now the multiplication on each of these just adds another g on the right. So this is gh, hg, hg, and hg squared. And so you can see, using this relation, whenever I have an h on the right, I can push it to the left through all the g's using this. And so you can fill in this whole multiplication table. I'm not going to do the rest. I encourage you to do the rest on your own. And when you fill in the whole multiplication table, you'll see that this multiplication table is the same as the dihedral group's multiplication table, if you plugged it in. So h is going to correspond, g is going to correspond to rotation by 90 degrees, and h is going to correspond to reflection across the horizontal axis, which is what we discussed at the start of the lecture today. Okay, so that's all I want to say about this case, when k equals 3. And that's sort of the end of the story for case 1, right? Case 1 is when h squared is equal to the identity, and we had all these subcases for k. So we dealt with k equals 0, 1, 2, and 3. So, we proved that GH has to take this form, and it has to be either 0, 1, 2, or 3. So we've now classified all the groups of the form when h squared is equal to the identity. And so we get D4 as one of my groups of order 8. Okay, so let's move on to the final case. The final case occurs when h squared is equal to g squared. And this should be very reminiscent of what we did at the start of today's lecture with the quaternionic unit group. because when I take the quaternionic units, G and H, G is going to be something like I, right? Because that's going to generate this cyclic group of order 4. And then all these elements have order 4 as well. And when I square any of these elements, I get -1. So the square of I is -1, and the square of any of these two elements is -1. So in case 3, we actually want to prove that we're just equal to the quaternions here. And so we want to do the same thing that we did before. I want to look at what happens when I do G times H. And this, for the same reason as before, has to be equal to H times G to the K. It can't be some power of G, because that would imply that H was also some power of G. So G times H has to be equal to H times G to some power of K. Again, K cannot be equal to 0, because then, K cannot be equal to 0, not for this reason, but because then G would equal to the identity, and that's a contradiction. Right, if K equals 0, then this element is the identity, so I can cancel it, and I get G times H is equal to H. So G is the identity element. If K were to equal 1, then G and H commute, and G is abelian. So now I want to actually prove that we're back in Z2 cross Z4 cross Z2. Right, we've already seen this group, it's this one. So how do I do this? Well, I'm gonna go back and define a new element, A equals H times G. Right? At some point, I chose an element H in my construction. Right? Choose any H of the that's not one of these things. So I could have chosen A instead, right? Because A is also an element that's not in this thing. And I want to show that if I chose A instead, then I would get A squared is equal to the identity, and I'd be back in this case. So I could handle whatever group appears here by looking at the previous case. So as I said, A could have been chosen as the other elements. So G can also be written like this. And when I square A, since G and H commute, A squared is H squared times G squared. But if H squared is equal to G squared, then this is G squared times G squared, and G has order 4. So A squared is equal to the identity, and I'm back in case 1, if I were to choose A instead of H. So this group is going to appear in that case list, and in fact, this is exactly the group Z2 cross Z4. So I've already shown that this group has appeared in my isomorphism class. The isomorphism class of this group, rather, has appeared in my list. So I don't need to worry about K equals 1. So what happens when K equals 2? Well, the same argument as before works. If K equals 2, then GH equals HG squared. And I'm in fact going to be back in the case when I have two elements that are conjugate that have different orders, right? G and G squared have different orders, but if K equals 2 in this equation, then you're going to get a contradiction. You can look back at the lecture just a few minutes ago and see that it's the same argument. So what's the last case? The last case, again, is K equals 3, and you can show, using the same sort of arguments previously, that this means that G is equal to this, is isomorphic to the quaternionic unit group, which is sometimes denoted this way. So the theorem is that every group of order 8 is isomorphic to one of these. Okay, so that's going to be it for today's lecture. I hope you're able to follow along, and at least that I've convinced you that these five groups are the only groups of order 8. As you can see, the proofs here get very sort of computational, right? You just need to check what the group multiplication looks like in each of the specific cases. But the way that you can build up the multiplication is by looking at specific elements in their orders, right? So we started getting deeper and deeper into the cases by trying to rule out certain orders, right? So we ruled out an order 8 element because once we had an order 8 element, we were this group. Once every group element had order 2, we were this group. And so these 3 groups are the groups with an order 4 element that's not order 8. We have an abelian one. This one's called a semi-direct product. And this one is actually called a simple group. And we'll talk more about those words. We'll at least talk about simple next time. Semi-direct product we won't probably be talking about, but this one is not simple. Okay, well, thanks for listening, and I will see you on Monday.